All right. So in today's video, we're going to focus on the idea of torque. We'll talk a little bit about center of gravity. So by the end of the video today, you should understand how torque affects the motion of an object. You ought to be able to calculate the torque produced by a force, and you should be able to learn. You should learn how to deal with the torque provided by gravity on an object. All right. Now, a lot of this, honestly, is going to be reviews from stuff we did in honors last year. But you really need to, I guess, understand torque in a little bit deeper sense than we did in honors. So I found that it is helpful to review. So please, even if you did well with torque last year, I encourage you to watch this, okay? I am, however, going to really try to focus on the basics. I don't know what I'm saying. Okay, here we go. So we know, hopefully by now at this point in our learnings, that net force causes linear acceleration, right? It changes the velocity of an object. All right. Similarly, net torque causes angular acceleration. So if you want to change how quickly something is spinning or change the direction that it's spinning in, that is going to require a net torque. All right. The symbol for net torque is the Greek letter tau. It's kind of a T with a wavy top. Sort of pi with one leg. Sometimes people make the bottom of it curvy. So either of those two notations are acceptable. All right. So if you want to change how quickly something is rotating, you're going to have to apply a force to it. But it's not just the force that that determines your torque. Where the force is applied and the direction in which the force is applied also matter. Okay. So let's do this. Oh man, shouldn't have gone that route. Okay, so the torque produced by a force is directly proportional to two values. The force being applied to the object, or the force applying the torque, all right? And it's worth noting here, when you're calculating torques, usually what you do is you calculate each individual, I shouldn't say usually, I think always. You consider each force independently and calculate the torque provided by that force. So if there are three forces, you're going to calculate three separate torques. And then we'll learn later on that you can add those up, just like you'd add vectors. Okay? So anyway, the torque is dependent on how much force is applied. It is also proportional to the distance between the pivot point and the point where the force is being applied. All right? That distance is usually called the lever arm. All right? And it brings up an important point, which is this. If you want to talk about torque, you have to talk about your pivot point, okay? The torque acting on an object about one pivot point is not the same as the torque about a different pivot point. So you have to consider that pivot point, all right? And I guess I should probably comment too that probably a more technical term for pivot point. In honors, I always use the word pivot point. But in AP, we'll probably, I need to start getting in the habit of calling it the axis of rotation, because it's technically not a point. It's a line that runs through your object, okay? Like the axle running through a tire or something like that. Okay? So to calculate torque, you have to use what's called a cross product, all right? So when we did work, we learned that work was force dot displacement, right? And so this was a method of multiplying two vectors, okay? And it gives you a scalar as an answer, right? There's no direction associated with work, all right? Conversely, when you calculate torque, you use what's called a cross product. It's a different mathematical way of multiplying two vectors. And the result of a cross product is actually another vector. And so you'll notice torque is a vector, okay? Much like angular velocity and whatnot, we will measure that direction as being either clockwise or counterclockwise. Okay. Now, there is a mathematical way to calculate a cross product using IJ notation, and I showed you that when we did work for the dot product. But over here for the cross product, I'm not going to worry about the unit vector notation way of calculating a cross product. It's really not that important. So, you may remember we had 4 different ways of calculating work. Because we're not going to worry about the IJ notation for torque, we're just going to have 3 different ways to calculate torque. All right. But in the same way that it was important to know all those different ways for work, it is going to be important that you know all the different ways for torque. All right, so here are the 3 ways to calculate torque. All right, option 1, you can multiply the magnitude of your lever arm by the magnitude of your force and multiply that by the sine of theta. And this is worth writing down. Theta is the angle between your force vector and your lever arm vector. Okay? So that's one way of calculating your torque. All right? Now, the other option is this. When you calculate torque, your force needs to be perpendicular to your lever arm, or at least part of your force needs to be perpendicular to your lever arm. And we saw that last year in honors, and I'll show you that here in a moment in an example. But so another way to calculate torque is to split your force into components, and then simply multiply the magnitude of your lever arm by the magnitude of the force, the component of the force that's perpendicular to your lever arm. Okay, so that's option number 2. All right, and then option number 3 is instead of splitting your force into components, to split your lever arm into components. And we're just interested in the component of the lever arm that is perpendicular to the force. All right, so that is option number 3. Okay, so there are 3 different ways to calculate torque. And any of those 3 will do. Okay, so right now this is just about a lot of words and numbers. I'm sorry, words and letters. So on the next slide here, we'll do an example, and I think it'll kind of come together. Okay. And then down here at the bottom of the page, it just kind of explains what the different variables are, right? And so let's make sure this is right. I just noticed a typo that I didn't catch. All right. So here's what all the things are. So again, theta is the angle between the force creating the torque and the lever arm. Okay. This, somehow I lost the notation here. This is supposed to say F perpendicular is the component of the force that's perpendicular to the lever arm, and D perpendicular is the component of the lever arm that's perpendicular to the force. All right. And also, it's worth noting that there's a shortcut here, right? If your force is perpendicular to your lever arm, then your theta is going to be 90, and the sine of 90 is 1. All right. And so if the force is perpendicular to the lever arm, this is huge. If the force is perpendicular to the lever arm, it's just torque equals the length of the lever arm times the force. Okay? And to be honest, in most of our problems, that's going to be the case. But you need to be prepared if it's not, because this is an AP, and you know, we got to know what's going on, right? So here we go. So here we've got this wrench. All right. And so what we're going to do is we're going to try to make it turn, all right? And usually when you try to make a wrench turn, there's a bolt or a nut or something down here that we're trying to make it turn around. So this, if you imagine a dotted line running through, you know, the center of this, that would be our axis of rotation, formerly known as our pivot point. I'm going to label it with a big fat P for pivot point, okay? So now to make this rotate, I need to apply a force, right? And so usually what you would do is you would grab the end of the wrench and push either down or up, all right? So let's say that this force here is 8 newtons, right? Okay, so to calculate that torque, I need to know the length of my lever arm. So this is where our pivot point becomes important, because our lever arm is, by definition, the distance from our pivot point to where the force is applied. So that's my lever arm vector. Okay? So to calculate the torque applied by this force, option 1 would be torque equals dF sine theta, right? So I didn't tell you the length of the wrench, did I? Let's make it 20 centimeters, 0.20 meters. All right? So to calculate our torque, we can go 0.2 meters times our force times the sine of, oh, look, here I'm applying my force, and it looks like it is perpendicular to my lever arm. So it's just times the sine of 90. So sine of 90 is 1. 0.2 times 8 gives you 1.6. The units here are Newton meters. It is not the same as a joule because it's no longer a cross product. It's now a dot product. So the units for torque for physics purposes are Newton meters, and that's what we'll use, okay? Now, if you wanted to use options 2 and 3, they're a little bit silly, right? Because option 2 was calculate, I don't remember which one was 2 and which one was 3, but whatever. Calculate the component of the force that's perpendicular to your lever arm and multiply it, right? Well, our force is perpendicular. So you just get, 0.2 times 8. And then similarly, number 3 is torque is find the perpendicular component of the lever arm and multiply it by the force. Well, again, our lever arm is perpendicular to the force, so you just multiply, all right? So these are all going to give us 1.6 Newton meters, all right? Now, what if the force had not been applied all the way at the end of the wrench? What if the force was applied, say, halfway down the wrench? Well, then the calculations are exactly the same, except your lever arm is now shorter, right? That would just shorten your lever arm down to, 0.1 meters or whatever, okay? So your lever arm is not always the full length of the object. It's simply the distance from your pivot point to where your force is applied, okay? Also worth noting then is what about this? What would happen if my force was applied right here? Well, if the force is applied right there, then my lever arm is 0, right? Because the distance from my pivot point to my force is 0, okay? And so using any of these 3 methods to calculate your torque will give you, in this case, a torque of 0 because the length of your lever arm is 0, okay? All right. So all of those examples were examples where the force was perpendicular to the lever arm, or in this last case, I guess the lever arm was 0. So let's do another example where maybe that's not the case, all right? Okay, so same exact setup. Here's our wrench. Here's our lever arm. It's still 0.20 meters. All right, so this time, for some reason, I have decided that I am going to apply a force right here, but I am going to push on it this way, okay? Or you could pull on it. I guess that wouldn't work though, because the wrench would fall off the bolt, but whatever. So I'm going to push on it this way with a force of 8 newtons. So think about that for a second. Before you do any calculations, think about it. You're pushing to the left. All you're doing is pushing the wrench into the bolt there, right? So you're not actually going to be producing, you're not going to be making the wrench turn at all, right? So our torque ought to be 0. So let's check it. Option 1, torque equals dF sine theta. So I'm going to have my lever arm, which is 0.2. I'm being sloppy about my units. My force is 8 newtons times the sine of, well, my lever arm points this way from the pivot point to the force, and then my force is applied exactly the other way. So that's 180 degrees. And the sine of 180 degrees is 0. Okay, so this is not actually going to produce any torque. Looking at option 2, torque is d times the component of the force that's perpendicular to the lever arm. Well, my force is perfectly horizontal, so there isn't a vertical component at all, right? And so that's going to, your F perpendicular here is 0. So this is d times 0 gives you 0, all right? And then the third option is the opposite. Find the perpendicular component of your lever arm and multiply it by the force. Well, there's no vertical component of the lever arm, so you get 0 times your force, which also gives you 0. Okay? So, if your force is parallel to your lever arm or anti-parallel to your lever arm, either one, then your torque is 0. Okay? So finally, let's do an example where we actually have to do a little bit of trig. All right, so, and boom, 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 boom. All right, so let's do this. Let's have a force applied this way. Let's keep our force at 0.8 newtons. No, it wasn't 0.8, sorry. Our force was 8 newtons. All right, and so let's make this angle in here be 60 degrees. Okay, so option 1 would be torque equals dF sine theta. So our d is 0.8 meters. Ooh, no it isn't. 0.2 meters times our force is 8 newtons times the sine of the angle between the two vectors, which here is, so you can make an argument here about whether this is 60 degrees or technically when you find the angle between your vectors, you're really supposed to place them tail to tail. So this should go like this, which then would make my angle 120 degrees. But it turns out with sine, 60 and 120 are what, supplementary angles, I think? They add up to 180. Sine of supplementary angles are equal anyway, so it doesn't really matter which of the two angles you use, okay? So there's a little wiggle room there, okay? So I'm going to go ahead and use 60 degrees just because it's a little bit more intuitive. So sine of 60 is not a half. I wish I had made that 30 degrees, because now I got to grab my calculator. In my notes, I used 30. So we're going to have 0.2 times 8 times the sine of 60, and you get 1.38 meters. Okay, slightly less torque than when the force was perpendicular, right? Because, I'm sorry, slightly less torque than when the force was perpendicular, because only part of the force is now actually producing torque. All right? All right, so that's that. So option number 2. Option number 2 says, let's calculate our torque by multiplying the length of the lever arm by the component of the force that's perpendicular to it. Okay? So what I would have to do is I'd have to say, all right, well, my force looks like this. It's 8 newtons at an angle of 60 degrees, right? And that's got 2 components. There's one component that's parallel to my lever arm and one component that's perpendicular to my lever arm, right? And so then what do I want to use? I want to use sine, right? So F perpendicular would be 8 times the sine of 60 degrees. You can see it's going to give you the exact same answer, right? So let's, I guess, go ahead and figure it out just for the sake of completion. So 8 sine 60 gives you 6.93. Okay, so the idea is this is the amount of force that's actually producing torque, not the 8 newtons. It's just the 6.93 newtons because the other part of the 8 newtons is parallel to the lever arm. Okay, so now my torque then becomes my lever arm, 0.2, times my perpendicular force, and multiply, and you can see it's going to give you basically the same answer. Okay. All right. So the third option here is kind of a weird one, and it doesn't really make a ton of sense in this problem. Like, it wouldn't be intuitive, I guess. It works, but it probably wouldn't be intuitive. I'm going to do it, and then my next example will be an example where it might make a little more sense to do it that way, perhaps. All right. Yeah. Okay. So here we go. Ooh, just got a message. Phone dinged. Done. What's the past tense of ding? Dung. All right, sorry. You probably don't know what I'm talking about. My phone just made a little beepy noise. I don't know if you heard it. Okay, so anyway, here we go. Physics, not phones. 3, torque. So this time what I'm going to do is I'm going to find the component of the lever arm that's perpendicular to the force. All right, so here's how that's going to look. Yeah, clean up my drawing here a little bit. So here's my lever arm, right? My lever arm looks like this, right? So what I want to do is I want to split this lever arm vector here up into components. One of them is supposed to be parallel to the force, and one of them is going to be perpendicular to the force. So how you draw this, I don't know. I guess you could probably, I don't know. There's 2 ways to draw it is why I'm hesitating here. So I guess what I would, maybe this will make it the easiest for you to see it. So here is a component of my lever arm that's parallel, and here is a component that's perpendicular. Notice my arrowheads. Okay. So now what I can do then is I know that D up here is 0.2 meters. So this D perpendicular, you can see it's opposite from this 60-degree angle, right? So once again, my D perpendicular is just going to be D sine theta. So that's where that theta comes in again, okay? So there we go. So what do you get? You get 0.2 times, so 0.2 times the sine of 60 gives you a number. 0.2 sine of 60, I'm really mad that I didn't use 30 degrees, 0.173 meters. And so now I can say, oh, well, my torque is being applied by a a force of 8 newtons, which perpendicularly is 0.173 meters away from that 8 newton force. Okay, and so multiply it out, and it gives you the same answer of 1.38. Oh, I'm realizing I rounded it wrong. It's actually 1.39, but whatever. Newton meters. Nobody cares. Okay, there we go. So, like I say, that probably would not be an intuitive solution to this. Okay, but sometimes your lever arm is at a weird angle. Aha, what if I gave you this? All right, so here, let's use the same lever arm. All right, and let's suppose that I pulled down here with a force of 0.8, I keep doing that, with a force of 8 newtons, and let's once again make this angle 60 degrees, right? Oh, well, that makes it a little bit easier for me to see that, oh, here's my perpendicular component on my lever arm, and here's my parallel component on my lever arm, right? And so then the math here, it's literally the same problem that I just did, but I just turned everything, you know, to make the wrench crooked instead of the force crooked, okay? All right, so finally, gravity. What do we do if there's gravity? All right, so here we've got this. We've got this board, oops. We've got this 20 kilogram board. It's 4 meters long, and the board is sitting on a support 0.75 meters from one end. So let's label this. Here's our 0.75 meters. That means that this distance is going to be, what, 3.25 meters, because the whole board is 4 meters. All right. The board is uniform. And I don't know why it says here that it's 5 meters long when it clearly says that it's 4 meters long. Okay, so who wrote this problem? Oh my gosh, just ignore this whole paragraph. Okay, okay, so here's our deal. The board is uniform, and Roy is kind of holding it. And so what I want you guys to do is calculate the torque produced by gravity. Torque produced by gravity is what? So in order to do this, we need to consider our center of mass, all right? And so remember, center of mass is an object's average position of mass, all right? So we talked about this when we did momentum and when we did position of center of mass, right? And so what you're going to do is you're just going to treat your object, your force of gravity on your object, as being located at your center of mass, okay? So if this thing is 4 meters long, that means that the center of mass is 2 meters from one end, which means that this distance here is 1.25 meters, right? And so what I'm going to do then is I'm going to go, oh, here's my force of gravity right at my center of mass. So my force of gravity is 20 times 9.8 is 196 newtons. And now I can calculate my torque, right? So I'm going to go, oh, here's my lever arm. It's the 1.25 meters, right? About this pivot point. I guess that's a badly worded question. It should say, what's the torque of gravity about our pivot point, you know, at the fulcrum. So I know my lever arm. I know my force. They're perpendicular, so I can just multiply, right? So my torque is my distance times my force, and it gives you 245 newton meters. All right. So finally, let's do one that's maybe slightly more complicated. Oops, that's the same slide. All right, so here we've got Thor's hammer. It's got a mass of 80 kilograms. All right, notice because the top end is heavy, the center of gravity is going to be higher up. So this little yellow star here represents our center of gravity. All right, so what we're going to do is we are going to calculate the torque produced by gravity on Thor's hammer about our pivot point, which is going to be this point here, right? This actually is going to explain why the hammer won't balance. It's going to show us why, if we let it go, the hammer will fall this way, okay? And it's because of the torque produced by gravity about this pivot point, okay? Cool. Now, so let's do this. So we can find our force of gravity, 80 times 9.8. Force of gravity, 784 newtons. And so now I can calculate the torque produced by gravity. So the torque produced by gravity is the distance times the force of gravity times the sine of theta between those two angles. So according to my drawing here, my lever arm is 0.4 meters because that is how far the star is from my pivot point. My force of gravity is 784 newtons times the sine of, well, let's see, if this is 70 degrees, then this is going to be 20 degrees. Aha, sine of 20 degrees. Okay, and that'll give us our torque. Okay. So 4 times 784 times the sine of 20. Ooh, somebody has come into my room. Who is it? Hello, Julia.
I was just doing my check-in.
I gotcha. 107.3. Sorry about that. So 107.3 Newton meters. And then obviously you could use any of the other methods. I think if I was going to, do it not using this equation, I'd probably use option 3, where I would say, all right, here's my lever arm, but just this much of it is perpendicular, right? So my perpendicular lever arm would be 0.4 times what? The cosine of 70, I guess, which is the same as the sine of 20. So, all right, so there we go. I guess I should comment on one other thing here on this drawing. This is maybe getting ahead a little bit and starting to move towards, move towards what we're going to need to know for equilibrium. But so I commented earlier that the force of gravity was what was going to make this thing tip over this way. That's only true. Well, I mean, it will tip over, but what's going on down here? If there's no friction, what will actually happen is your center of gravity will go straight down, and the rest of the what do you call this thing? Hammer will rotate around it. Okay, so that the top end of the hammer would kind of go this way, the bottom end of the hammer would kind of go this way. Okay, but if there's friction, then the bottom end can't slide, right? And so that's when it would begin to tip over. So let's think about that. So if there's friction down here preventing the bottom of the hammer from sliding, it wants to slide that way, so I guess the friction would have to actually be this way, right? This is a total tangent. I don't know why I'm doing this right now, but whatever. So no, I shouldn't say that. This is important. So how much torque is applied right there by friction? That wouldn't be providing any torque, right? Because it has a lever arm of 0, okay? Right, because if this is my pivot point and this is my force of friction, that would not provide torque, okay? And so that's where the torque provided to make it tip over comes from, is from gravity. Oof, all right, cool. Have a good day.